Hello students, welcome all to my YouTube channel. In this video, I'll be solving the 26 WBSET previous year paper booklet X series, and today in this video I'll be showing you solutions to question number 11, this one, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So question number 11 to 20 I'll be showing in this video. So let's start. We're solving question number 11, which is a question on Hamilton. So let's see the solution here. We are given a Hamiltonian system with generalized coordinate Q alpha and conjugate moment P alpha. Okay, we know that Q alpha for some specific alpha equals to alpha naught is an ignorable or a cyclic coordinate. So what is an ignorable coordinate? That means that the Hamilton does not depend on Q alpha naught. So this is important. What is an ignorable coordinate? Means the Hamiltonian does not depend on Q alpha naught, means delta H by delta Q alpha naught will be equals to 0. So look at the options. Where do we have delta H by delta Q alpha naught? But what is delta H by delta Q alpha naught? P alpha naught, P dot alpha naught. So P dot alpha naught is in B and in D. Now from B and D we have to choose. So we discard this option is discarded, and this option is A and C is discarded. Now let us see. So P alpha naught dot is equals to 0. Okay, now next step, equation for Q alpha dot naught is delta H by delta P alpha dot naught. So we can see this satisfies equation number B. So Q dot alpha naught here, Q dot alpha naught equals to, this is the formula, delta H by delta P alpha naught. So our option B is the correct option. Solution number 12. For what choice of n the following transformation in phase space can be canonical? QP represents generalized coordinate and generalized momentum respectively. P equals to Q to the power n sin 2p and Q equals to Q to the power n cos 2p. So here we have to find the value of n for which the transformation can be a canonical transformation. So that is the question. Let's look at the solution. The given solution is P. So P, value of P and value of Q is known to us. So for this transformation to be canonical, the Poisson bracket must satisfy QP equals to 1. What is Poisson bracket? What is the formula for Poisson bracket? Del Q by del capital Q by del small q, del capital P by del small p, minus del capital Q by del small p into del capital P by del Q should be equals to 1. So let's calculate this. Del Q by del capital Q by del Q, we'll have we'll differentiate this. So n q n minus 1 cos 2p. Again, capital Q with respect to small p will have minus 2qn sin 2p. You all can differentiate this, very simple. Now capital P will differentiate with respect to small q, will get n q n minus 1 sin 2p, and del P, capital P with respect to small p, will get 2qn cos 2p. Now we'll compute the Poisson bracket. So we'll replace here the del Q by del, here you can see del capital Q by del small q, this thing, del capital Q by del small q, this thing will replace here. Okay, it'll come here. And then del capital P by del small p, del capital P by del small p, this thing we will replace here. Similarly, del capital Q by del P, this one will bring it here. Okay, and del capital P by del capital Q, this one we will bring it here. Now when you solve this and you multiply this, you will see that you will get 2nq to 2n minus 1 cos square 2p plus 2nq to the power 2n minus 1 sin square 2p. We will take 2nq, 2n minus 1 common. Then inside the bracket we'll get cos square 2p plus sin square 2p, which is equals to 1. So we are left with 2nq, 2n minus 1. For the transformation to be canonical, we must have, this is the main thing, 2nq, 2n minus 1, this thing should be equals to 1. So for this this must hold for all q, which means the exponent of q must be 0. This exponent of q must be 0. So this exponent of q will put is equals to 0. 2n minus 1 equals to 0. 21. So n value C is the correct option. Question number 13 is a question of Laplace transform. We are given a differential equation here. This is a differential equation given to us. dy by dt plus ay equals to e to the power minus bt. We'll take the Laplace transform on both sides. Laplace of dy by dt plus a into Laplace of y equals to Laplace of e to the power minus bt. Now using the standard Laplace properties, Laplace of dy by dt is s capital Ys minus y0. So this we will replace here. Instead of this, it will come here. We'll replace this Laplace of dy by dt. So now we are substituting. So here Laplace of dy by dt is s ys minus y0 plus, now here a into Laplace of y will become ys equals to Laplace of e to the power minus bt is 1 by s plus b. We'll be solving this further, putting the initial condition y0 equals to 0, y0 equals to 0, we put the equation. So here y0 will become our 0, y0 will turn 0. So I left with sys plus ays equals to 1 by s plus b. Ys will take common and s plus a will come in the bracket. Ys is 1 by s plus a into s plus b. Option A is the correct option. The domain of convergence of summation n equals to 0 to infinity n square bracket z square plus 1 by 1 plus iota whole to the power n is, we have got this 4 options. This is our question. The given series is a power series of the form n equals to 0 to infinity n to the power p r to the power n. So this is the standard form of power series where r is equal z square plus 1 by 1 plus iota. So if you apply the ratio test or the root test, the power series will converge absolutely for mod r less than 1. This is the main thing you all have to remember. Thus the given series converges when, what is our r? Our r is z square plus 1 by 1 plus iota. So we'll put the mod less than 1. So z square plus 1 mod and 1 plus iota mod is given by 1 square plus 1 square under root, which is root 2. So z square plus 1 is less than root 2. Option B is our correct option. Solution number 15. The number of zeros counting multiplicities of pz, 3z to the power 5 plus 2iz square plus 7iz plus 1. So this is our pz. In the annular region, z belongs to complex numbers, mod z less than 1, less than 7 is 1, 2, 3, 4. So let us see our annular region. This is our annular region. This is a circle of radius 1 and this is a circle of radius 7, and this is the annular region where we have to calculate the zeros of our function. Now here we apply the Rouché's theorem. Rouché's theorem is very important in complex analysis, and every year we get questions from Rouché's theorem both in CSI net and set. So if mostly we get, if fz and gz are analytic in a domain containing a simple closed curve, and if mod gz is less than mod fz on C, then fz and fz plus gz have the same number of zeros. Here we have to divide the main pz function into two smaller functions, gz and fz, such that mod gz is less than mod fz. This is important. So I repeat, pz is our main function, and this pz, whatever pz is given to us, we have to break it into two different functions, gz and fz, such that mod gz is less than fz on C. Then fz and fz plus gz will again give us the entire pz. Then fz and fz plus gz have the same number of zeros inside that annular C. So we apply this theorem to two contour. First we have to apply this to z, mod z equals to 7, the bigger one, larger contour, and then mod z equals to 1, the smaller contour. Okay. So pz, our 3z to the power 5 plus 2 iota z square plus 7iz plus 1. So let us apply first in the larger contour for z, mod z less than 7. So 3 mod 3z to the power 5 is 3, 7 to the power 5, 2i z square is 2 into 7 square, 7iz is 7, mod I is 1 and 7, and this mod of 1 is 1. We see that, suppose this is our fz and this is our gz. This is our fz and this is our gz. Then by Roche's theorem, pz and 3z5 have the same number of zeros inside mod z less than 7. So fz we take as mod 3z5 and gz we take as 2iz square plus 7iz plus 1. 3z to the power 5 has one root, z equals to 0 with multiplicity 5. So we will see that this is in the question they are asking, you have to count with multiplicities. The number of zeros will be 5. Now we go to the next one, counting roots in mod z less than 1. So for z equals to 1, we have mod 7iz 7, 2iz square 2, 3z5 3, and here fz we take as, we change our function, fz will take as 7iz and gz will take as 2iz square plus 3z5 plus 1. So here we can see fz is greater than gz, then fz has one root because here z power is 1. So it has one root in mod z less than 1. So pz has one root in z less than 1. Since there are 5 zeros inside mod z less than 7 and 1 zeros inside mod z less than 1, the number of zeros in the annular region is given by, we will subtract both the zeros, 5 minus 1. So option D will be the correct option. If you are watching my video and you have come till here, please like, subscribe and comment so I get motivated to make more such videos for you all. Thank you. Question number 16. Which of the following is false? An entire function maps bounded set to bounded sets. A non-constant entire function is unbounded. A non-constant entire function maps unbounded set to unbounded set. And there exists an entire function has infinity as its regular point. Solution. Let's see all the options one by one. A. Let f be an entire function, then for any bounded set B, fb is bounded. So this is true. This is from the properties of entire function. It's if a function is entire, it will map bounded set to bounded set. Now B. By Liouville's theorem, a bounded entire function must be constant. This is a very important theorem of complex analysis. Liouville's theorem that entire function, if it is bounded, it can only be a constant function. So our option says a non-constant entire function is unbounded. This is also true because non-constant will be unbounded. If it is bounded, it will become constant. So this is our true option. Let's go to C. C says that a non-constant entire function maps unbounded sets to unbounded set. So we'll discard this with, we'll use an example. So let us consider fz as sin z. This is a entire function and domain is R, that is a set of real numbers which is unbounded. So domain of sin z, we can put any value in z. So it is the entire R. The range lies between -1 to 1 which is bounded. So C is false. And last option. So for example, we take fz equals to z. Okay. The function is entire, and if we make the transformation omega equals to 1 by z, then f omega equals to 1 by omega, which is well defined except at omega equals to 0, which corresponds to z equals to infinity. Thus, infinity is a regular point for fz equals to z. Option D is true. And what is a regular point? Definition of a regular point. A regular point or ordinary point of a function is a point where the function is well defined or analytic and does not have any singularity. So we see polynomials do not have any singularity only at infinity. Solution number 17. Which of the following is not true? So it is important. Not true, we have to see. Eigenvectors of distinct eigenvalues of a Hermitian matrix are orthogonal to each other. This is property of Hermitian matrices. So this is true by the property. Unitary matrices have eigenvalues of the form e hydra theta where theta is real. This is also true by the properties of unitary matrices. Eigenvalues of real symmetric matrix are real. True. And eigenvalues of a real symmetric matrix are not necessarily real. This is our false. As we know, eigenvalues of real matrices, real symmetric matrices are always real. Question number 18. Let T from R cube to R cube be a linear transformation defined by T of ABC equals A plus 2B minus C, B plus C and A plus B minus 2C. Then the nullity of T is 1, 2, 3, 0. Now let us look at the solution. The null space of all vectors that satisfy T ABC equals to 0, 0, 0. This is called the nullity. Now we have to solve the system of equations. A plus 2b minus c equals to 0, b plus c equals to 0, and a plus 2b minus c, a plus b minus 2c equals to 0. So rewrite c equals to minus b. From equation number 2 here we can see that c equals to minus b. Substituting c in 1 and 2. So we have to replace c equals to minus b in equation 1 here and equation 2 in both the equations. So a plus 2b minus of minus b, a plus 3b equals to 0. So a equals to minus 3b. Now instead of a and a will replace minus 3b, and instead of c we will replace minus b. So we have t of abc is minus 3b, b and minus b. B is our free variable. So since as there is only one free variable, the null space is one dimensional. So A is correct. Option A is the correct option. Alternatively, there is one more way in which we can calculate the nullity by rank nullity theorem. So here we take the coefficients. We see the three equations given to us. So here coefficient of A is 1, here 2, and here minus 1. So we construct a matrix and then we take out the rank of that matrix. Here using the three equations which is given to us, this is the matrix form. Then apply to take out the rank, we have to reduce it to Euclidean form. So we will subtract R3 such that R3 minus R1. So we'll get 1 2 minus 1 0 1 1 0 minus minus 1, and R3 is R3 plus R2. Then we can see that the last row becomes 0. We get 2 Li rows, so rank will be 2. Then by rank nullity theorem, the rank of T plus nullity of T is equals to the number of columns or the dimension of T. So it's R cube, so dimension is 3. So rank plus nullity is 3, so nullity is our 1. So both ways we can do the same problem. Question number 19. Suppose T1 and T2 be the linear operators on R square such that T1 x1 x2 is equals to x2 x1. So it is swapping operator, and T2 x1 x2 equals to x1 0. It puts all the second coordinate x2 will be 0. So the four options are given to us. So let us do with the help of an example. It will become very fast. X1 x2 will take us 2 3. What does T1 do? It makes x1 2 3 2 3 2. This swaps T1. And T2, what does it do? 2 3, it maps it to 2 comma 0, because the second coordinate it makes, the transformation makes the second coordinate 0. Now let us compute the composition T1 T2. So to compute the composition, first we'll compose T2 and then we'll apply T1. So first apply T2. T2 of 2 3 is 2 comma 0. And T1 will be the swapping operator. This is 0 2. Now compute T2 T1 opposite. So first we'll apply T1. T1 is the swapping operator. So T1 will map 2 3 to 3 2, and T2 will make it 3 0. We can clearly see that these two are not giving us the same result. So we can clearly see T1 T2 is not equals to T2 T1. So option A is our correct option. The Fourier transform of a function fx is defined as f of k equals to minus infinity to infinity f of x e to the power minus ikx dx. This transform converts a function from the time domain or spatial domain into the frequency domain. So our function fx is given by e to the power minus x square. So our fk will become minus infinity to infinity e to the power minus x square into e to the power minus ikx dx. Now we have the well-known result of a Gaussian function minus infinity to infinity e to the power minus ax square e to the power minus kx dx is root over pi by root over a e to the power minus k square by 4a. Our a is equals to 1, so replacing a equals to 1 in our Gaussian function, fk will become root pi by root 1 e to the power minus k square by 4. So option B is the correct option.